Hi, and thank you for tuning in to the virtual version of my match meeting talk. Today, I will tell you something about a rather unusual problem that connects quantum information theory with pure mathematics and statistical physics. This talk is based on these two papers in collaboration with Adrian Kent, Dmitry Chistikov, and Mike Patterson. And I will also show you some preliminary numerical results by my PhD student, David Yamas. The motivation for this work is to study more general Bell inequalities. Consider, for example, the simple case of entangled spin 1/2 particles. Typically, Alice and Bob have a finite number of measurement choices. For example, 2 measurement choices in the CHSH setup or n measurement choices in the Brownston Cave setup. What we want to do here is consider Bell inequalities that involve a higher degree of randomness. And the motivation is to allow for more efficient distinction between classical and quantum correlations. To this end, Adrian Kent and Damian Petalua-Garcia proposed the following setup. Alice and Bob choose their measurement axis completely at random, and the only constraint is that the angle between the two axes is fixed. A local hidden variable model that corresponds to this setup would be simply a coloring of the block sphere. So here this is illustrated in the case of Alice and Bob, and the two colors, green and white, would denote the two possible spin states, spin up and spin down. If Alice and Bob measured the spin along the same axis, then of course they would have to measure opposite spins. And so this implies that the colorings of the two spheres are inverted with respect to each other. And also each spin is antipodal, which means that opposite ends of one axis have opposing colors. Now our goal is to construct local hidden variable models that exhibit maximal anti-correlations and thus in a natural sense represent the best possible classical simulation of the singlet quantum state. So for instance, here if Alice chooses this axis and Bob chooses this axis in the fixed angle theta from Alice's axis, and they have measured the opposite spin, then the same direction on Alice's block sphere would correspond to the same spin state as her axis. This setup is particularly relevant for quantum cryptography, since increasing the randomness within Alice and Bob's choices would give an adversary who might want to tamper with or somehow intercept and resend the signal less information about the protocol. Now, finding such an optimal coloring seems like a difficult task, and because of that, I would like to first consider a simpler version of this problem on the plane. And the problem goes like this. Imagine you're given a bag of grass seeds from which you can plant a lawn of any shape that you like, but a fixed area. Let's say it has the area equal to 1. And then a grasshopper will land at a random point of this lawn. And after that, the grasshopper can make exactly one jump of fixed distance d and in a completely random direction. So for example, if the grasshopper started out here, then the jump could bring it to any of the points on the dashed circle. But if the grasshopper started out here nearer the boundary, then there is a certain probability that the jump will bring it outside of the lawn. So the question that I want to ask is, what shape should your lawn have to maximize the probability that the grasshopper remains on the lawn after the jump? And we want to answer this question for different fixed values of the jump length d. So at the beginning, our intuition was that probably for small jumps, the lawn will have a round shape, because that is the shape that minimizes the boundary given an area. But actually, we found numerically that the optimal shapes don't look like a disk, but instead they look something like this cogwheel shape, where the distance between the cogwheels corresponds approximately to the length of the jump. We found this optimal shape numerically, but we also can prove analytically that the disk is in fact not the optimal shape for any jump length. So how do we numerically find these shapes? So the idea here is to map the continuous mathematical problem onto a statistical Ising type spin model. So we put our continuous space onto a grid, and each grid cell represents sort of a discrete pixel of the plane. And it can take one of two possible values, depending on whether this area is occupied by the lawn, which would be spin 1, or not occupied, which would be spin 0. Then we want to move these spins, so these pixels, around to find the optimal shape of the lawn. For this, we use a heuristic search algorithm called simulated annealing and also related algorithms like parallel tempering. And these algorithms are very powerful in finding extrema of badly behaved complicated systems. So the idea here is that we attempt to move a lawn pixel to a different position, and if that improves our probability, then we accept this change. But if it makes our probability worse, we still have a certain chance to accept this update, and that is based on an artificial temperature parameter that we introduce. So at high temperatures, we kind of move around a lot and explore our configuration space. But then we slowly decrease the temperature, and in the process of the slow cooling, we become less and less likely to accept not advantageous updates. And so the hope is that in the end, in case of a successful simulated annealing search, we actually converge onto the global extremum of functional. So here's an example for such a simulated annealing run for the actual planar grasshopper problem. And you can see that even though we started out with a very chaotic random system, as the temperature cooled, we have converged to this regular cogwheel shape. Now, the number of cogs and the shape of these cogwheels do depend on the length of the jump. And we studied this dependence, and we also studied what shapes come up as the jump length increases further. So we observe a kind of phase transition from this cogwheel regime to a critical regime where we have a multitude of very interesting shapes with very unusual symmetries. Then we have a so-called three-bladed fan regime, a regime where the shapes resemble stripes and so on. So these were very interesting just in their own right statistical results on the plane, but kind of coming back again to the circle and the sphere, which are more relevant to the Bell inequality setup and to quantum cryptography. We have also obtained some analytical results for these cases. And I also want to mention that apart from spin measurements, these can also be experimentally realized with projective polarization measurements on photons. So for the circle, we found that in almost all cases, optimal lawns actually have probability that equals to 1. Or in other words, local hidden variable models can produce perfect anti-correlations. The only exception are antipodal lawns with jumps that are a certain rational multiple of pi. And this implies that even the slightest inaccuracy in the angle allows for classical simulation of quantum correlation. For the sphere, we have showed analytically that in analogy to the planar case, hemispherical lawns are also almost never optimal, exception being jump angles of a certain rational form. And this means that on the sphere, more sophisticated local hidden variable models can be constructed, which will lead us to novel types of Bell inequalities. Now, what do these shapes on the sphere actually look like? Here, again, we did a numerical study, and so these are some preliminary results for the optimal configurations that my student David Yamas has obtained. And you can see that similarly to the planar case, you have this kind of cogwheel regime, but we also obtain other regimes such as these labyrinth or stripe faces, kind of combinations between the two. So to give you a little outlook, we keep working on this very interesting and fascinating problem. I want to study in more detail the planar grasshopper problem, and also it is very interesting to generalize it to higher dimensions. Here are some preliminary results by my graduate student for the flat 3D space. And you can see that actually in contrast to the 2D case, the rotational symmetry of the initial problem is preserved in the optimal shapes, which are simply the ball, or for larger jumps, the ball that develops a hole in the middle. So this breaking of isotropy does not actually seem to happen in higher dimensions. We're also interested in generalizing this problem to other spaces, not just the surface of the sphere, but perhaps the surface of the torus, to other metrics, such as the discrete metric. Continuous lawn densities are also very interesting. And setups that are relevant to quantum information are also pairs of lawns or an extension to multiple independent jumps. Finally, there is a really fascinating application to pattern formation or morphogenesis. So as I mentioned, even though the original system is completely isotropic, so the Grasshopper has a uniform probability to pick any direction of the gem, the shapes that we obtain break that symmetry. And actually very similar shapes are predicted for dipolar interacting quantum gases in a completely different setup. Here I'm showing from these papers some calculations of ground state density distributions for trapped Bose-Einstein condensates that have this dipolar long-range interaction. And so it seems that there is some connection between the long-range interaction in these cold atom systems and this unusual Grasshopper-type long-range interaction in the Ising models that we're considering. And this connection would be extremely interesting to explore. Thank you very much for your attention. Please check out our papers as well as our YouTube channel and let me know if you have any questions.